Well, Assalamu alaikum dear students. I'm Engineer Abdul Basid and we are in lecture number 27 of week 14. The topic we are going to cover in this video tutorial is seepage and Laplace equation. Okay, so talking about the seepage first of all. So in the previous tutorial, in the previous chapter actually, in the permeability topic, we have discussed the seepage phenomena to certain extent, that is what is seepage and how it will be developed in water retaining structures. Like for example, we have dam structures are barrier to stop the flow of water or to retain the water in a reservoir. So then how the seepage is developed, why it is being developed, and what are the consequences after the seepage is being developed. Okay, so it is a thorough discussion about it. For example, we have a dam structure and a barrier is constructed from the earthwork, okay, and that is to stop the flow of water, okay, and to store the water behind that barrier in a reservoir. Okay, so then that water, for example, here it is the water, here is the practical example, this is that model. Okay, so you can see the water is present over here, and this is that barrier constructed for the for as the dam wall. Okay, this is the earthwork. Okay, then let's say why the seepage is developed. For example, there is pervious layer present over there in case of dam structure. So in the dam body, in the main wall, there will be core walls and lining over there and properly compacted earthwork, so there are no chances of seepage. Okay, less chances of seepage, you must say. Okay, but from the bottom, from the bed of the reservoir, you can see there is at certain length from that of at certain distance from that of the wall, you will have a pervious layer. Okay, and that pervious layer will start that seepage to happen through it, and then it will go through the dam structure, or you can say go under the dam structure, and it will be emerged on the other side, and that will ultimately reduce the slope stability on the downstream side of the wall. Okay, so this is that seepage that is normally stated as under seepage. Okay, but sometime when the lining is not proper compaction is not provided, so the water will find its way out for to pass through this main body of the dam. Okay, and that type of seepage is called seepage through. Okay, or through seepage. Okay, so then what will happen if the seepage is in this phenomena? So you can see that this is seepage flow. So initially the seepage will be like very difficult to determine, and it will be very negligible type of seepage. Okay, because the water will try to find its way to go out through on the downstream side. Okay, and it will be difficult for the water to initially make its way out. Okay, and that will be like possible with the help of the interlinked voids in the soil, so sample air in the soil reservoirs and these dams and these walls. Okay, so initially it will be difficult, but after some time when the water keep on passing through these voids and find its way, so thus this piping will happen. Okay, and the water will properly make a pipe type of way for its flow out through this dam wall or under this dam wall. Okay, and then this seepage water will emerge on the downstream side at some distance from the wall. Okay, and that will happens to be like the sand is boiling and the sand will be raised at that point. Okay, and a huge pipe will happen. Okay, so this is their situation initially. In this practical picture, you can see that the water is stored behind this wall, and that is that some seepage is happening through it, and that has become a big issue, and now the water is flowing through this wall in a big amount. Okay, and that will ultimately you can say reduce the strength or the stability of this slope on the downstream side, and it will demolish this wall ultimately. Okay, so then you can say seepage is like a big issue to deal with initially when you are working on the dam structures. So here in this chapter, actually, the seepage is a phenomena that needs to be discussed. So I already have given you a thorough discussion, thorough idea of the seepage. Then we will work on the Darcy law, and that is how to calculate the seepage through the soil using Darcy law. And then we will work on the flow net. Okay, as the water flow through the soil sample is not uniform in all the directions, and not uniform throughout the area that is perpendicular to the flow, so that's why there is a need of a new type of calculation that may be flow nets. Okay, and the concept of the flow net is actually derived from the Laplace equation of continuity. So we will derive this Laplace equation, and also we will discuss the applications of this Laplace equation, and then some problem on the seepage phenomena and the Laplace equation. Okay, so this is what we are going to cover in these seepage chapters, as this is a new chapter after permeability. So here this is again the same thing we have already discussed it. Then coming to that Laplace equation. So let's say, let's take an example. For example, we have a soil that is practically present on the field, and we have installed a sheet pile, a single sheet pile, okay, here to stop the flow of water or to stop the seepage of water. Here on the upstream side we have a water level that is H1, and on the downstream side we have the water level that is H2. Okay, initially when the water is passing through this soil sample, when there is no sheet pile, so the water will follow this way. Okay, as my cursor is moving, so the water will follow this way. Okay, but after the installation of this sheet pile, the water will follow this way. This water will be first seeped through this soil sample and will come to a point where there is no sheet pile installed anymore. So that depth will be achieved, and then the water will flow through it. Okay, so hence a new type of phenomena, that is flow lines, flow nets, and equipotential lines will be developed. Okay, so we will discuss about it in the next topic. Okay, here we need to have to derive the Laplace equation first of all. Okay, Laplace equation of the continuity. So let us consider this type of assembly is provided, and now if we are having the calculation or derivation, so for that we need to have a block of the soil sample that is represented over here, that is A block, and that is having a height of dz. Okay, and that is having a width of dx, and out of the plane in the y direction, okay, out of the page, it is having an axis that is y axis. Okay, and that y axis is having a width of dy. Okay, so it is a cube. Okay, a block, a cube named as A, and this is having a height dz, width dx, and a thickness that is out of the plane, that is dy. Okay, so now discussing this thing in a magnified form, so we will have, this is that A block, and this A block is in the magnified form presented like this. Okay, so you can see it here that this is dy. Okay, this is out of the plane dy, and this is dz, which is the height, and this is dx, which is the width. Okay, so this is the dy I was talking about earlier. Now whenever the water is passing through it, it will have certain velocity, that is that discharge velocity Vx, as this velocity is in the x direction, this is x direction, so this is the horizontal flow velocity, then this is Vx. Okay, so the area that is perpendicular to this Vx can be visible from this simple thing. Here it is, let me draw it first. Okay, let me do it. Here it is, this is that area I am highlighting it. Okay, this is that area that is perpendicular to this Vx. Okay, and that is dy multiplied by dz. So I hope this is clear to you now. Okay, now the area that is perpendicular to Vz, this is that velocity in the vertical direction, this is that velocity in vertical direction. Okay, and the area that is perpendicular to that vertical direction flow is this dx multiplied by this dy. Okay, so here this will be the area. Here I am plotting it now. This is that area that is perpendicular to the flow of water in the vertical direction, which is velocity vz. Okay, so this is that continuity equation requirement. If you have any idea of that, continuity equation tells us that the discharge through a soil sample or through any pipe or something, that will be equal to the velocity multiplied by area perpendicular to the flow. Okay, so here it is the discharge through the soil sample, which is Vx multiplied by the area dz dy. Okay, so this is that area, and here in this direction the discharge is equal to, this is the velocity Vz, and the area is dx multiplied by dy. Okay, now this is that inlet velocity, that is that velocity at the inlet, at the inflow of the area of the water. Here it is. Okay, this is that outflow in the x direction, and this is that outflow in the y direction. Okay, so here in the x direction the inflow is Vx multiplied by dz dy, and the outflow is Vx plus, this is that small velocity change in the velocity occurred at this small distance, change in horizontal distance, and this is that dx, which is the derivative of this thing. Okay, so this small velocity that change occurs through this block, this small block, this is not this much, I have magnified it for simplicity. Okay, then this is that velocity n velocity, and the change in velocity occurs at this level, that is that small change in the velocity with respect to some small distance. Okay, and that is the actually the function of the x, so that's why dx is multiplied over here. Okay, so now this inside the bracket term is actually the velocity, and that is multiplied with the area, so dz dy is again the same area. Okay, so this is that inflow velocity, this is that outflow, in here in the vertical direction this is that inflow velocity, and this will be the outflow velocity. Okay, and that is vz plus change in the velocity in the z direction with respect to small distance z. Okay, and that is the function of dz as well. Okay, so this is multiplied with area, and that is dx dy is the area. Okay, so I hope you have got the phenomena of this inlet and outlet velocities. Okay, so now let me talk about this derivation now. Okay, here it is, all these things are given as I was discussing earlier. Okay, here it is, you can see that for flow at point A, so this discussion is about point A. Let me change this color to make it a bit more visible to you. Okay, here it is. Okay, now the consider an element that is the block A, already I've told you, and that is having dimension dx dy dz. This is the same discussion. Dy is the perpendicular to the plane out of the paper. Okay, it is known as it is shown in the enlarged scale, so already I've told you how to show it in enlarged scale, and this is Vx. Vz is the component of the velocity, discharge velocity, in the horizontal and vertical direction. So I was talking about this thing. Then the rate of flow of water into the element of the block, that is, this is that inflow. Okay, our rate of the flow into the element, that is Vx dz dy. So this is that inflow, and this is that inflow in the vertical direction. Okay, now the outflow in the vertical in the horizontal direction will be this thing. This is that outflow velocity. Okay, and multiplied by this thing, this will become the discharge in the outlet. Okay, and this is that discharge in the outflow, discharge of the outflow through that block A. Okay, so I hope this is clear to you now. Now here it is, you can see, assuming the water that is incompressible, let's say we have assumed that the water is incompressible. So when the water is incompressible, then continuity equation tells us that the velocity at any point will the discharge at any point during the flow will remain the same. Okay, so when the discharge is same, so the difference of the discharge between 2 points will be equal to 0. Okay, so this is that simple thing. Let me get back to that drawing mode now. Okay, here it is, my drawing mode. I hope this will be visible now. There it is. This is visible. Okay, here you can see this is that you can say this is that outflow, okay, velocity, and this is that outflow discharge in the x direction. This is outflow discharge in the in the z direction, and this is that inflow. So the outflow discharge minus inflow discharge is actually the difference of the discharge at two different points. Okay, and that will be certainly equal to 0. Okay, this is actually shown by the continuity equation. Okay, earlier we have discussed it in the fluid mechanics as well. Okay, so then this equation, after solving this equation, this will give us this thing. Okay, after thorough calculation, this is that result we are getting from this calculation. Okay, so this is the change in the velocity with respect to that x-axis with any change in the x-axis distance, and here it is the change in the velocity in the z direction with respect to distance covered in the z direction. Okay, so this is the final solution from this equation. Now Darcy law actually tells us that the discharge velocity can be expressed as, okay, how it can be. The Darcy law tells us that velocity is equal to ki, and k is the hydraulic conductivity and I is the hydraulic gradient. Okay, so I is actually equal to the change in head with respect to the distance covered. Okay, and k is already very well discussed in the previous tutorial, that is hydraulic conductivity. So in the x direction we will have this equation, and in the y direction the velocity will be equal to k z I z, and that will be equal to this change in head with respect to this thing will be the again the same thing, the same equation. Okay, so now talking about this phenomena, here it is. Okay, this velocity is equal to this thing. Again I've written the same equation. Okay, now putting that values in this previous equation, that is this equation. Okay, change in velocity with respect to x direction and with respect to y direction. Okay, so putting this vx over here and this vz over here. Okay, so already this is in derivation and this is derivation, so this will give us double derivation with respect to the z axis. Okay, so here it is the double derivation of h, okay, with respect to x axis, and this is the double derivation of x with respect to y axis after putting these values in this equation. Okay, so this will be square square square, as this is double derivation. Then now let's say kx and ky, the hydraulic conductivity for the isotropic soil. Isotropic soil actually refers to that type of soil where the velocity actually the properties of the soil remain the same in all directions. All direction refers to in the x direction, in the y direction, and in the z direction. So if the properties of the soil are actually same in all the directions, then the hydraulic conductivity will remain the same in all the directions. So that is kx is equal to kz will be equal to ky. Okay, so now if these two values are equal, then dividing it by kx or kz both side of this equation, then kx and kz will be get cancelled with the with each other, and this will be the final equation that we will get a this is the double derivative of the head with respect to x and double derivation of the head with respect to z is equal to 0. Okay, so this is the equation we are getting it now. Now here it is. In the next lecture actually we will discuss about the flow nets and how to draw this flow net, and what are the application of the flow nets, equipotential line and flow lines and all these calculations in the next lectures, inshallah. Or I hope you have got something new to learn from this tutorial. Thank you very much. Assalamu alaikum.